term. Multiply to get my third term. Multiply. James.
Yeah, half.
Yeah, so for this specific problem, I see that there is a value that I multiply by the first term to get the second term. And it's the same value that I multiply by to get the third term. And then it's the same one to get the fourth term. Do you see, John, do you see how each time I'm multiplying by a half? So we would say that the factor, or the R value that's changing each time that we multiply by, not changing, but that changes our terms, is 1/2, because each term gets multiplied by a half to get the next term. Now, what do you think A is based on my definition? Andrew, what's my A value here? Yes, it is. A is the first value in the series that starts us all off, but it has to appear everywhere else. So 1 times a half, and then 1 times a half times a half, right? And so 1 actually turns out to be my A value in this series. Beautiful. Let's try the second guy. What number do you have to multiply by each time to get the next term? Kayla, do you want to guess on that guy? So from 3/4 to 3/16. 1/4. Very beautiful. Very nice. So R is 1/4 because each time I'm multiplying the previous term by 1/4 to get the next term. And Max, what's my A value? What's my first term? 3/4. You'll see very quickly that finding the R value and the A value becomes very important when we talk about convergence and divergence of series. But geometric series aren't always listed out like this. Sometimes we look at these forms here, where it has an n value to start, where it's written in A sub n terms, the general form. In that case, everybody does it a little different, but I actually like to list those first 3 terms anyways. I always like to say, okay, what is really happening? And I like to look at the first term, the second term, the third term. Maybe more terms if needed, but I always like to list out my first couple terms so that I can say, what's my A value and what's my R value? So let's see if we can't generate that for these two guys. So we want to figure out what's our A value and R value, so we're going to list out the first couple terms here. So I'm going to start by letting n for this problem starts at n equals 0. James, if n is 0, can you tell me what my first term is going to be if I'm letting n be 0?
It's going to be 7, isn't it?
Close.
No,
It's going to be 5/1, right? And then 2 to the 0, right? Yes. And so in other words, it's just going to be 5/1, which is just 5. Yep. So my first term is 5. You did. That's okay. Yep. So that's when n is 0. Drew, when n is 1, can you tell me what that has to be? When n is 1, what does that give me? No, that's okay. Sorry. No. 25 over 2 to the, hang on, when n is 1, I do get 25 because I have 1 plus 1. And on the bottom, I have 2 to the negative 1. Yeah. Good. That's okay. This is learning moment. I want to make sure we are all getting this. And so help me with these negative exponents, Andrew and John. What do? If I have a negative 1 on the bottom with a 2, I can either write it as 1/2 or I could, 2 to the positive 1 on top, right? So if I wanted to rewrite it into something more tangible, I would do something like that, right? So let's do one more. Everybody write down your third term. When n is 2, let's see. On top, you would have 5 to the third. And on the bottom, you would have 2 to the negative 2, which if I want to rewrite it into something manageable, I could think of that as 5 cubed times 2 to the second. Okay. So that's enough for me to say, okay, I have a pattern. I'm looking for two values. I want my R value, which is what I multiply each term by to get the next term, and I want my A value, which is the first value. John, you want to give me the A value? What's my first value? 5. So A is 5 for this, right? And Max, do you got an R for me? It's tricky. 10. Absolutely, it's 10. Because each time I'm multiplying both by a factor of 5 and I'm multiplying by a factor of 2. So my R value becomes 10. Does that make sense to everybody? Do you see that? So why don't you guys try the last one? And I'll walk and see if you guys are getting the right A and the R. So for D, 7 times negative 1 to the n over 3 to the n. Be careful. Notice what you're starting at. You're starting down here with n equals 2. So list out your first couple terms for me, and then find your A and find your R. Okay, so I want you to go back now. We're going to go back to the previous example, and I want you to tell me, does each of those A, B, C, D series converge or diverge? And if it converges, what's its sum? So we're going to go back to question 1, A, B, C, D, those parts. We're going to determine if the series converges or diverges. And if it converges, find its sum. And the two pieces we're going to focus on right here is the absolute value of R less than 1. And if it is, it converges, and it converges to A over 1 minus R. So I'm going to put that in here next to my things. I'm going to put a little note right here that if the absolute value of R is less than 1, then that means my series is converging. And not only does it converge, but it converges to the sum of A over 1 minus R. So I'm going to wander and see if you guys can do this. I think many of you can. You're going to see if there's an R value less than 1, and then plug in A and R and get your sum if it is, okay? So I'm going to wander. Let's see. So I want to see. So R is 1/2, which is less than 1. And that means my series does converge. And it converges to 1/2. Nope. It converges to 1A over 1 minus R. And the second one, R is 1/4, that's less than 1, so this guy converges to 3/4 over 1 minus 1/4, or 3/4 divided by 3/4, which is just 1. So the second guy converges to 1. And Andrew, you told me, what about that third one?
That one would diverge.
Yeah, your R value is 10. 10 is not less than 1, so that means that series diverges. And the last guy. John, did you get the last guy?
No, not yet.
Not yet. That's okay. No worries, because I know I'm going super fast here. So is this less than 1? Well, that's 1/3, which is less than 1, and that's true. So this guy converges, and he converges to 7/9 over 1 minus negative 1/3. So when your R value is negative 1/3, you have to be really careful in there, right? If your R value is negative 1/3, it's 1 minus negative 1/3, which will go plus. So your R value, so that's 7/9 over 1 plus 1/3, which is 7/9 over 4/3. So what's the sum? 7/9 times 3 over 4. That cancels. Did you guys get that this converges to 7 over 12? I think that's what I'm getting to. Any questions? I want to look at when you see series with just, I want to look at a special case of geometric series where both n and x are in your series. So does anybody have any questions, though, on a basic geometric series? What it looks like, how you find it, how to find a, r, or a sum. These are pretty good, aren't they? They're kind of fun. The geometric series are kind of fun. So let's take a look at a geometric series where it also has a letter x in it. Now, how do I know it's a geometric series? Because notice n is appearing in the exponent, right? And so what do I do myself? When I look at this geometric series, we want to find a and r and where it converges. Does it converge, and if so, where? So I'm just going to start by listing out a couple terms in this geometric series. So I'm going to start by letting n be 1. And I'm going to put my first term when n is 1. And what's that give us? Negative 2 times x. What happens when I put a 2 in there? I get negative 2 squared. And then when I put a 3 in there, I get negative 2 cubed. So each time in that series, it's going from positive to negative, but both my numbers and my x's are changing. These types of series where your x increases in powers each time is actually given a special name. This is actually what we call a power series, and power series are defined as like infinite polynomials. So power series are defined mainly when you have x to an nth power. So x to the first, x to the second, x to the third. So I think of power series as infinite polynomials. We're going to devote 2 sections on this in our thing, but this is just a glimpse. This is just a glimpse right now to show you how you can also use geometric series with a power series. So can you guys tell me what the r value is and the a value for this thing right here, this geometric series? What's my a value, John? My a value, my first value. The first one, just the first term.
It's just negative 2x.
It is negative 2x. That's my a value. Yes, it is. Beautiful. And Max, what do I have to multiply by? What's my r value? It is negative 2x because it's weird, right? So hang on, let me color these different colors. Hang on, let me color these different colors. Yeah. So, let me change my background. Now it's good. Okay, so let me color these different colors. So yeah, so my r value is what I multiply by each time. So each time I have to, no, undo, Tina, slow down. My a value is my first term. My r value is what I multiply by each time to get the next one. And Max, you told me that is also negative 2x. So this particular power series is funky. My a and my r both have x, which makes sense because x is changing. So now, what does it mean for a series that has x in it to converge? Remember, x is a variable, and it can stand for a number. So if x happens to be 0, let's just say x is 0. My sum becomes 0 plus 0 plus 0 plus 0 plus 0, which automatically converges. If x is 10, then it's negative 20 plus 400 minus something, then it diverges, right? So x can be different things. Our job is to figure out what x's make it converge. So how are we going to do that? Some people that worked on this in recitation on Monday. How do we figure out if this thing converges? What do?
We set up an inequality.
We set up an inequality. In order to figure out if this series converges, we focus on the R, and we want to make sure that that R value, the absolute value of that R, has to be less than 1. In order for the series to converge, the R value has to be less than 1 in absolute value. And the absolute value of negative 2x is going to be the same as the positive absolute value of 2x. And Andrew, do you remember back from algebra, how do we solve an inequality? Do you know? Drew, do you remember how we did this Monday? Did you do this Monday with me?
I didn't.
You didn't get that far. Oh, okay. Okay, Max, you're the only one that was here yesterday. What do we do to fix this, to finish this? The absolute value of 2x is less than 1. Do you remember?
We divide each side by 2.
We do divide by 2, but before we get there, we have to do this. Did you do this? Where you set it up. So what does this mean? If you go back in time to algebra or to Professor Montgomery or Professor Deutschenoff, you guys were in Calc 1 last semester, I think, and you had lab. And hopefully they went through these absolute value inequalities. I don't know if you remember. But what this is saying is it's saying that there's a distance less than 1. What this is saying is that you are within 1 unit of 0 on both sides. So you're looking for all the numbers that fall within 1 unit away from 0. That's kind of what you're doing. And so what that does is it bounds you on 2 sides. You want to be 1 unit on the left and 1 unit on the right. Absolute value is distance. In physics, it means the absolute value, it means your distance, your absolute value. It could be positive or it could be negative, but you want to be within 1 unit on each side. And so, yeah, Max, to solve this tripartite, it's called a tripartite, I'll put the word up there, or a 3-part inequality, it's called a tripartite or a 3-part inequality. And the way we solve that is by dividing each term by 2. And so that tells me that negative 1/2 is less than x is less than 1/2. How many of you guys remember doing this? Do you guys kind of remember doing this a little bit vaguely? You're going to get really good at this. Trust me. By the end of next week, you guys are going to be solving these inequalities just like that. Like, I remember this. I know how to do this. All right. So what does that mean? In order for the series to converge, x has to fall in between negative 1/2 and positive 1/2. So we would say that the interval of convergence, this is terminology, the interval of convergence is, and we use our interval notation. How do I rewrite negative 1/2 less than x less than positive 1/2? Kayla, how do we do that with interval notations? We use open brackets, right?
Yeah, and then it's negative 1/2 to 1/2.
Negative 1/2 comma 1/2. Pictorially, that means that in my picture, as long as x is some value in between negative 1/2 and positive 1/2, so x can be any number in there. It could be negative 1/4, it could be positive 1/3, it could be negative 1/6. As long as x falls in that band, in that interval, the series will converge, because when you put that value up in x, you'll get an r value that is less than 1. Now, not only is WebWork going to ask you for what we call the interval of convergence, but we also want to talk about the radius of convergence. And this becomes important when we talk about errors and things in physics and engineering, when you talk about errors and estimations and things. So we want our radius of convergence. What do you guys guess is the radius of convergence for this interval here? What would you guess? Yeah, it's 1/2 because the radius is just half of your interval distance. Whatever your whole interval distance is, the radius is just half of it. So you would say that the radius of convergence is just half of this whole distance. This whole distance is 1, so the radius of convergence is 1/2.
Is that the same thing as the sum?
No, we got to get the sum. Okay, so here we go. So we have a power series. Interesting things about power series is that x is in it and x can change. So as long as x falls within -1/2 to +1/2, this power series will converge. The radius of convergence is 1/2. And as long as x is in this interval, the sum of the series is going to be, so let's get that sum. What's it going to be, Drew? It's going to be,
-2x.
yes it is, over,
1 plus 2x.
yes it is, absolutely. So if this series does converge, so if I'm in between -1/2 and +1/2, then my series converges to this sum. So we would say that in this interval, -1/2 to +1/2, the series converges to, and my sum has a variable in it because remember, the sum is going to change depending on what x is. So my sum will have a letter in it. Does this make sense? Do you guys see that? So power series are special cases of geometric series. I want you guys to practice one more power series. And more than anything, this is getting us ready for the stuff we're going to talk about next week. So let's do one more power series, and then we'll talk about the very last test in this whole section, which is called the divergence test. So I want you guys to go ahead and try this next example. X minus 5 to the n over 6 to the n. N starts at 0 and goes to infinity. I want you to find the following elements. I want to know what is my a value, what is my r value, what is the interval of convergence, in other words, what values of x will cause this series to converge. I want my radius of convergence, what is half the distance for that interval. And finally, on this interval of convergence, what is the sum of the series? So a bunch of things we need, and I'm going to wander, and then you can ask questions. I will note, as you're starting this example, note that n starts at 0 for this. Fast. All right, let's see. I'm going to list out a couple terms. So my first term actually turns out to be 1. My second one turns out to be x minus 5 over 6. My third one turns out to be x minus 5 squared over 6 squared. So I can see right away, a is 1, r is x minus 5 over 6. And to get my interval of convergence, I need to take r, or the absolute value of r, and make it less than 1. So I need the absolute value of x minus 5, making it less than 1. And we just talked about how to solve these inequalities, these three-part inequalities. Going back to previous knowledge, we multiply each part by 6, and then we add 5. And so you guys should be getting that your interval is -1 to 11. That's what you got, right, Drew? That's what you got?
Yeah.
John, you got that, right? Did you get that? It's 2. Multiply each term by 6, add 5 each time. Okay. And then, yeah, let's see. I might have gone way Oh yeah, you're
No,
good.
it isn't.
You're good.
Roll
You're
over.
good. You're good. You're good. You have to. Yep. Good. And then, how'd you get your radius? You found the distance. So I'll just write it in there. But to get your radius, right, we're going all the way from -1 to positive 11. And so this whole distance is 12 units. And so half the distance is my radius, which is 6 units. So that means my radius of convergence is 6 units. And you're going to use this, you'll use this a lot. When you get into Calc 3, if you take Calc 3, your radius of convergence is, when you go 3 dimensions, isn't just like a little line, it's actually like a circle. So you have a radius of convergence that's actually a circle. It's kind of cool. It's really kind of cool. All right, so on the interval of convergence, what does the series converge to? The sum of the series is a over 1 minus r. So that's 1 over 1 minus x minus 5 over 6. Did anybody simplify that down? I think if you get a common denominator and simplify it all down, I think you get to 6 over negative x plus 11. So I would say that the sum of my series is 6 over negative x plus 11. Anybody have questions on this special geometric series? So in summary, when you have a geometric series, you can find an a and an r value. You know it's a geometric series because n appears up in the exponent, and that helps you create this geometric series effect. And we know how to find an interval of convergence if we have a letter x in there, a power series. All right, so let's talk then. Let me cross that off on the board. Okay, so in order for an infinite series to converge, the terms have to be shrinking. Here's an example. For instance, let's take an example. If I give you the infinite summation n equals 1 to infinity of, let's just say, n, what's happening to these terms is these terms are just infinitely growing, right? And that thing diverges because it's a sum. I'm just adding more and more values. I can also look at something like 1/2. And if I want 1/2 to be added to 1/2 to be added to 1/2, again, over time, that sum is just growing and growing and growing, right? 1/2 plus 1/2 is 1, plus 1/2 is 1.5, plus another half is 2. This thing just grows and grows and grows infinitely big, and it diverges. So this statement here that if something converges, the terms have to go 0, right? In order for this to converge, your terms, these terms that you're adding each time, they have to be getting smaller, right? If I don't make these guys go smaller, I have no way for the sum to converge. So you need your terms to get smaller. So that creates for us that contrapositive statement, right? If then, if such and such, then such and such, says if not such and such. So if our terms do not get smaller, or in other words, if the terms do not get smaller, if the limit as n goes to infinity is not 0, then the sequence does not converge. The sequence diverges. So based on a fact that if the series converges, the terms have to be going to 0, we make the opposite statement. If the terms are not going to 0, then the series cannot converge. It has to diverge. So let me take this divergence test and show you how it gets applied. We look at this example here. We have an infinite series. First thing I want to note, is it geometric? And how do I know if it's geometric? Is this geometric, Andrew? Question. Is it geometric? Do you guys know?
I don't know. I zoned out.
It is.
Oh, no worries, no worries, no
No,
worries,
it
no
is
worries.
not.
I thought you knew what it was
It
right
is
away.
not. There's no end in the
It's not geometric. Thank you. You're awesome. I love you. You're like my son. My son, all he does is classes. Anyways, don't worry about it. That's because it. Anyways, so sorry, I didn't mean to call you. I didn't know that you were done that.
No, you're good.
So if n is not up in the exponent, then it's not going to be geometric. I zone out all the time. Trust me, I do too. So if n is not in the exponent, it's not geometric. So if it's not geometric, we want to see if it's telescoping. Telescoping is when things cancel, but that bottom doesn't factor, so I can't write it as things canceling. So I want to look at this and say, okay, I want to say, well, what do I see right away? Are these terms even getting smaller? Are they heading to zero? Because if they're not heading to zero, well then I know this thing diverges and I don't even have to think any farther. So what happens if I take a limit as n goes to infinity of this nth term? What happens to these things? It does what?
You approach 1/2.
Yeah, this sucker, this limit is 1/2. You can either use L'Hopital's rule because it gives you infinity over infinity, and you can apply L'Hopital's rule twice, okay? Or the other way, and this is the way that I did in my calculus classes, is we said if it is infinity over infinity, the infinities are coming from the highest degrees. And so we can cheat, and we can just look at the highest degrees, n squared and 2n squared, and that allows us to look and say the limit is 1/2. That means these terms, as you're adding numbers, the numbers that you're adding is going to head to be 1/2. You're heading towards adding 1/2 each time. That's not 0, and so that tells me that this series diverges because those terms are not heading to 0. If the terms don't head to 0, the series diverges. That's how simple the divergence test is. Done. So, what do we learn? In this section, there are 3 specific types of forms that we've talked about. Telescoping, where the inner terms cancel. We spent all last class on telescoping. This time, we introduced geometric a little bit, and then we also introduced this divergence test. So I'm going to give you a worksheet right now. Everybody's going to get a worksheet. And we're going to work this worksheet. And on this worksheet, you've got 1, 2, 3, 4, 5, 6 different series. I want you to figure out which one of these is telescoping. And if it's telescoping, does it converge or diverge? Which one of these is geometric? If it's geometric, does it diverge or converge? And if it's not telescoping and it's not geometric, I want you to apply the divergence test, okay? So I'm just going to write down. I would look for geometric series and I would start there. Why? Because they're the easiest. So I would always start by looking for geometric series, and that's when n is in the power. That's a clue. Find A and R, and that'll tell you if it does it or not. And then telescoping, that would be the second guy I would look for. And in a telescoping series, you're looking for something minus something because you want terms to cancel as you list them out. And then you want to find the nth partial sum and figure out what happens as n goes to infinity. That's how you look at telescoping series. And then finally, if it's not geometric and it's not telescoping, then you want to apply the divergence test. So this first section gives you a lot of meat. It gives you a lot of different pieces to it. Yeah. This guy is geometric. And this guy is geometric. And this guy's going to be telescoping. And this guy is telescoping in disguise.
part do you have to take E to telescopes?
This one, the natural log one?
No, E. The fourth one.
E. Oh, you have to take it far. Oh, I should have changed that one. If you want to change the numbers, well, it's too late now. I got to change that on my notes. You have to go far on that one. You actually have to go far on that one. I have to change that on my notes, so I fixed that because it goes too far. You have to go like 4 terms out for it to start canceling. I was going to change that, but I forgot to do that. Sorry about that.
Is there a reason that you can't just like log out?
Yeah, because what's the natural log of 1?
0.
0. Okay. So, does it tell us anything if the terms go to 0? It doesn't necessarily converge. If the terms don't go to 0, it diverges. But there are going to be series that don't converge. In fact, P series. So, like if I give you this series right here, the harmonic series, the terms go to 0, but this thing doesn't go to 0 fast enough.
Okay.
So this is an example. This is the classic example that shows when you have terms that go to 0, but they don't go to 0 fast enough.
Got it.
How you doing? Got a limit for me here? Arctan. Remember what arctan looks like? Arctan looks like, what does he
Isn't it
look like?
the horizontal?
It looks like a tangent sitting on its side, kind of, right?
Does it go to 1?
Ah, well, let's think. Let's think.
Or
Let's
is it
think.
like,
Let's think this through. Tangent does this. And when you do tangent function, what's your x-axis? Your x-axis are angles, right? Angle measures. Pi over 2, pi. So when you go to look at the arctangent, you're just flipping x's and y's. So when you do the arctangent, So when you look at arctangent, yeah, arctangent. So if you look at that guy, it looks like goes up to pi over 2, goes down to negative pi over 2, and arctangent does that. So yes. So what'd you say, John? It goes to what? Pi over 2? Arctangent, as n goes to infinity, goes to pi over 2. What's 4 divided by pi over 2? Yeah. Let me see. So this is 4. So that's 4 times 2 over pi, right? Just 8 over pi. And that does not equal 0. And therefore, this series diverges by the divergence test. And those other ones are tricky. The geometric series, let me see if you guys are doing that geometric series. A is 2/3, R is 2/3. Since 2/3 is less than 1, this geometric series converges.
On the test, you're gonna want us to solve what converges to.
Yep, on the test you'll be solving what it converges to.
Okay.
Right now we're kind of just focusing on putting everything together. Yep. Did you list out some terms for that bottom geometric series?
Yeah.
Did you let n be 1, n 0, n be 0?
Then it would be 1, then it would be 2.
What do you get? When n is 0, do you get negative 3?
Yes. Yeah.
And then the next term would be 2 times, just 2.
Yeah, just be 2.
And then minus, n is 3. Wait, n is 1, n is 2. 2 squared times 3 to the negative 1,
Yeah.
which is like 1/3.
Yeah.
So that's
4/3.
over 3. And the next, yeah, that's minus 4/3. And then the next guy would be plus, so that this is when n is 0, this is when n is 1, this is when n is 2, this is when n is 3. When n is 3, n is 3, I have negative 1 to the 4 times 2 to the 3rd over 3 to the 2, or 3 times negative 2. So I can see what my a is. My a is negative 3, but my r value looks, did you get r is negative 2/3? I think my r value is negative 2/3. What do I multiply by one term to get the next term? And then the absolute value of negative
Yeah, it'll be
2/3, yeah, is 2/3, which is less than 1. So this series, this geometric series converges. Huh. That's the last one. Now those telescoping ones and that middle one, those are the hardest. Those are the ones that are really tricky. So on the board, that way I can just list them out here. So what terms did you get, James?
First I got 2 minus 1/8.
2 minus 1/8. Uh-huh.
And then the next term.
Wait. When you let n be 1, did you get 16? Oh, no, 1/8. 2 over 16. Yes, good. Go ahead. And the next guy?
Was a half minus 2/25.
A half minus 2/25. Okay. And the next guy?
2/9 minus 1/18 and 2/37.
2/9 minus 1/18.
Yeah, or 2/32.
And then what'd you get next? What was your next guy?
Next one was 1/8 minus 2/49.
1/8. Minus 2/49.
Yeah,
Okay. So, but what you noticed right here is that right here, this guy cancels, right? So he cancels, and there's my pattern. This second one cancels, skip 2 terms, and get to that third term. So this guy's going to cancel, this guy's going to cancel, this guy's going to cancel, because they're all canceling to the right. And then we go plus, dot. Now here's a trick. Those first 3 aren't canceling because there's nothing, well, okay. Second terms cancel to the right. First terms cancel to the left. So there's nothing for those 3 things to cancel with. So we're left with those 3 numbers, 2, a half, and 2/9. And that means at the back end of the series, you also have to be left with 3 terms left over when you're finding the nth partial sum. And so that means you need to figure out the 3 terms at the back end, which is a sub n minus 1, and a sub n minus 2. So you have to have 3 terms at the back end to match 3 terms at the front end.
the first pattern, yeah, it's just the sequence through that.
Since we know they cancel to the right, can we just skip the first terms? Because we know those would be canceled out.
The first terms cancel to the left.
The left.
The second terms cancel
We know
to
they
the
cancel
right.
left. Can we just skip those and we're doing?
If you want to, you can. So the second terms cancel to the right. The second terms cancel to the right. So there's going to be nothing for this guy to cancel with to the right. There's going to be nothing for this guy to cancel with to the right. And there's going to be nothing for this guy to cancel with to the right. The other ones are going to cancel to the left. So I know this is all messy. Let me put my sum. So it looks like for this telescoping series, which is letter E, it looks like your sum, the nth partial sum, is, what is it? 2 plus 1/2 plus 2/9, and then minus 2 over n plus 1 to the second, minus 2 over n plus 2 to the second, and then minus 2 over n plus 3 to the second. And to find out if a telescoping series converges or diverges, we look at the nth partial sum and find out what happens as n goes to infinity. So as n goes to infinity,
So all those n terms equal to 0, right?
yeah, those n terms all go to 0. But your web work problems actually make you list out these these last terms so they understand and make sure that you're understanding how to get there. So they all go to 0. And so we would say that this series converges. And the cool thing about geometric series and telescoping series is you can actually determine what it converges to. That's the cool thing about telescoping series and geometric series. So that's E. Yeah. And then you guys are working B. Did you get answers for the natural log one? This one. Yes, it does. Actually equals E. It actually equals E.
Oh,
It's weird. I know, it's so weird. How you doing? This is tricky. This is tricky. So for B, you want to use logarithmic properties.
Yeah, I know. Natural log would be.
Yep. So for that guy, for B, I know it's all smushed. I didn't leave enough space in here. So F converged and was geometric. E converged and was telescoping. D diverged. A converged, it was geometric. B was the telescoping in disguise, and so if we list out the terms on that guy, you'd get the natural log of 2 minus the natural log of 1 plus the natural log of 3 minus the natural log of 2 plus the natural log of 4 minus the natural log of 3. So lots of things are canceling out. In fact, natural log of 2, which is the first term, cancels with a second term. The first term cancels with the second term. The first term cancels with the second term. So we're going to be left with this guy. And then at the back end, I only have one term I'm worried about. Let's see. At the back end, what's happening? So my first terms are canceling to the right. So this first term would be canceling to the right. So the other one is going to cancel. So that means that my nth partial sum is just minus the natural log of 1 plus the natural log of n plus 1, which is just, this is just 0. And that tells me that the limit as n goes to infinity of the natural log of n plus 1 is infinity. So that tells me this, for part B, it's a telescoping series that diverges. And this guy, C, that one's the tricky one.
So wait, you said B then?
Yeah, B diverges because as you take n, because your nth partial sum turns out to be the natural log of n plus 1.
Yeah.
And that, as n goes to infinity, diverges. Like you thought, James, because you were looking at those terms.
Well, they'll never be zero, so they have to keep adding something to it.
Yeah, so just like you said, that guy diverges. And the last one is C. And C is taking the limit as n goes to infinity of 1 plus 1 over n to the nth power. And this is when, see if this looks familiar. See if this looks familiar. This is when we would say, let's let y be the limit as n goes to infinity of 1 plus 1 over n to the n. And then let's take the natural log. So then we'll take the natural log of the limit as n goes to infinity, and the natural log on this domain is continuous, and so we actually get n times the natural log. Nope, undo. So we get the limit as n goes to infinity of n times the natural log of 1 plus 1 over n. I did a couple steps there. And that gives you infinity times 0, which is bad. And that's when you have to use L'Hopital's rule. And so what you try to do is get it to be a fraction. So we rework this limit into a fraction. See if this rings a bell. Do you remember doing this on your homework? Kind of. You had some sequences problems where you actually went and you reworked this to put this as 1 over n. And then you took a derivative on top and a derivative on the bottom, and you applied L'Hopital's rule. So we did derivative on the top, and we did the derivative on the bottom. And when you get that, you get the limit as n goes to infinity of 1 over 1 plus 1 over n times negative 1 over n squared over negative 1 over n squared. And so you get the limit as n goes to infinity of 1 over 1 plus 1 over n. And I know because we did these on our homework, this just gives us 1. But then you have to remember you were at the natural log of y equals 1. And so that means y is equal to e to the 1 or just e. So what does that tell me? That tells me, the nth term divergence test tells me that the limit as n goes to infinity is equal to e. That is not 0, and therefore the series diverges by the divergence test. This pattern, again, comes up a lot of places. Economics, when you talk about compound interest, okay, this is continuous compounding. This comes up. So this comes up in nature when you talk about things happening over time, when you talk about exponential growths and decays. So this pattern here equals E as n goes to infinity. Question.